Hello. In this video, I'm going to talk about how resistors behave when they're placed in series with each other or in parallel with each other, and then work an example of a fairly complicated circuit where you can use some of these ideas to make it easier to understand what's happening. So first, let's take a look at if we have two resistors in series with each other. So here's a circuit, one resistor there, one resistor there, some battery here, one resistor, and a second resistor. Okay, so this is a series setup. And in series, the current is the same through both resistors in series. There's only one path for the current to flow. So if I were to draw current flowing in the circuit, I, like so, the current through the first resistor and the current through the second resistor will be the same. But the voltage splits. So voltage splits across the resistors, so that in this case, we have some battery voltage V. The voltage across the first resistor plus the voltage across the second resistor will be the same. So I could write that generally as here, V1, the voltage across the first resistor, plus V2 equals V in this case. And I guess I could say in the current case, the current is equal to I1 is equal to I2. So the currents are the same while the voltage splits. If we wanted to do a little bit of circuit analysis here, we would talk about the equivalent resistance of the circuit. And we can derive this expression, but I'll just write down and then try to provide a little bit of intuition. So the equivalent resistance of the circuit, if I were to try to turn this system with two resistors into an equivalent one with one resistor, that would look like this. So if I were to battery in a single resistor, which has an equivalent resistance, Req, to the circuit above, Req would be the same as just summing the resistances, R1 and R2, which probably feels intuitive. For an idea for why this feels intuitive, we could recall this expression. So recall that for some kind of, for resistors that we've looked at, the resistance of any given resistor is the resistivity rho times the length of the resistor, L, over the cross-sectional area of the resistor. So when you put two resistors in series with each other, one way to conceptualize what's happening there is you're really just creating one long resistor with the length of R1 plus the length of R2. And so in this sort of expression where you're calculating the total resistance, you're really just increasing the length. That won't always strictly be true, but it is a conceptual, intuitive way to think about what's happening and to think about why you're just adding resistances. Because when you add length to a resistor, you just linearly add resistance. The longer the resistor is, the bigger its resistance is. And so in series, adding another resistor is basically just making a longer resistor. And I think intuitively, that's something to hold on to conceptually. All right, so that's the series case. Let me make a line here to talk about the parallel case below. So let's look at the parallel case. So parallel. All right, so that could be a circuit that looks like so. One resistor here, and then another branching path for a resistor here. So some voltage R1, R2. All right, So in the parallel case, we have current flowing from the battery, but now the current splits. So there's some I1 splitting along this section and some I2 splitting along this section. The way it splits will depend on the value of the resistances, but it's true that the current splits in the parallel case. So you don't have the same current in general running through both resistances. And I could write that generally like I1 plus I2 equals I. So that if I have I coming from the battery, the current splits, but the value of that split current has to add up to the original current. Oops, I called that I1, but I really just wanted to call that I. All right, so current splits, but the voltage is the same across both resistors. Voltage is the same. All right, so Y. So if I had some voltage of the battery in this case, that's going to be equal to the voltage drop across both resistors. Why is that the case? Well, on this side of the circuit here, on this left side, we just have wire. So there's no voltage drop at all here. So the voltage on the wire on the left side of the circuit has to be the same as the high side of the battery. And let's just call that V. So there's some voltage V on this side of the circuit on the left side. Meanwhile, on the other side of the circuit, it's another wire connecting everything over here. So the voltage has to be the same everywhere because there's no voltage drops anywhere along this wire. So if there's 0 volts on this side, but there's V on this side, V volts, say a 9 volts for a 9-volt battery, then the voltage has to drop from 9 to 0 as it crosses this resistor and this resistor. And so there's 2 paths for current to go, but the voltage has to get from 9 volts to 0 in both cases. So the voltage drop has to be the same, basically because both resistors share a common wire on either side. And we can talk about that a little bit more. We could also try to analyze this circuit using an equivalent resistance idea. So that would look maybe something like this. So if we want to simplify it, we might say, okay, there's our battery, and now let's try to represent this with some equivalent resistor. That's just a single resistor that represents how much equivalent resistance the whole parallel system has. In this case, it turns out that 1 over R equivalent is equal to 1 over R1 plus 1 over R2. This is less intuitive than above, but I'm going to try to give a little bit of intuition. As an example for how this could work, so let's say above we had a R1 of 5 ohms and an R2 of 10 ohms. What would be the equivalent resistance in that case? Well, then we'd have 1 over R equivalent is equal to 1 over 5 plus 1 over 10. If we put all of that over a common denominator, we're going to get this is equal to 3 over 10. And then inverting, R equivalent is equal to 10 over 3, which is about 3.33 ohms. So the reason why I worked it through numerically in this case is because we can see that the equivalent resistance is actually less than the resistance of either resistor, which is kind of funny if you look at it the first time, but 3.33 less than either resistor. Okay, so what's going on there? All right, so here's the intuition. The intuition is, if we recall again our expression here, R equals resistivity times length over area. So again, resistivity is some material property that tells you how hard it is to push current through some particular kind of material, times the length of the resistor divided by the cross-sectional area of that resistor. In this case, adding resistors in parallel is like increasing the area of the resistor. So it's like putting two resistors side by side, so there's more area to pass through. So let me write that down. Adding resistors in parallel is like putting two resistors right next to each other, increasing their cross-sectional area. So what that means is when I have, even though I have two resistors, the effect of that is basically just increasing the area through which current can flow. And so overall, my total resistance for the circuit, when I work it down into this equivalent resistance kind of format, will be a lower resistance than either of them. Because basically I have one resistor with a bigger area, so therefore the total resistance has to be less than either of the individual resistances. So that's kind of a tricky idea, but I think boiling it down back to this basic equation helps intuitively. This won't always be exactly true, because I could have, you know, resistors of different material, so different rho values or different lengths, and so it won't be exactly the same as just straight up increasing the area in this equation. But it's a good intuitive way to hold on to what's happening and to explain why the equivalent resistance would be less than either of the individual resistances in parallel. Okay, so that's a basic rundown of how things work in series and in parallel. And now I want to give you an example of how you can use these ideas for some circuit analysis. So let me pull up that example real quick. Okay, so I've got a circuit here that's more complicated than either of the ones we used to introduce series and parallel as ideas. I've got a battery here, and then I have a parallel circuit where one leg is R1, but then the second leg has two resistors on it. And so this is different, and we can't use just series addition or parallel addition straight up. The goal of analyzing a circuit like this would be to figure out how much current is flowing in each leg of the circuit, and then what's the voltage drop across each component in the circuit. So the goal of this kind of circuit analysis is to figure out the current everywhere and everywhere, and also to figure out voltage drops across each component for each component. That's kind of where we're going. And the technique we're going to use is we're going to take sections of the circuit, turn that into equivalent resistance, and then simplify the circuit again until we have something that we know how to work with, basically. Okay, so let me show you how that works. So the first thing we're going to do is we're going to look at this section of the circuit by itself. Because here on this leg of the circuit, no matter what's happening on the left-hand side, all of that stuff, this part of the circuit is just a series circuit, plain series circuit by itself. So no matter what the voltage drop is from here to here, we know that the voltage drop across R2 and R3 has to add up to that, whatever it is. And we know that the same current passes through R2 and R3. So we can treat this as just a series circuit and figure out what the equivalent resistance would be if it was if we wanted to represent it as just a single resistor. So we're going to redraw the circuit as a battery, a resistor R1, and then an equivalent resistance over here, which I'll call R23. Okay, so R23 is just the sum of R2 and R3 because they were in series with each other. So here R23 equals R2 plus R3 which is just 5, given the values over here, R2 and R3. Okay, so now I have a purely parallel circuit. That's nice. And now I can write an equivalent resistance here for these two based on our equation for equivalent resistance. So if I keep going down here, now I can draw this as a single resistor, which I'll call R123, the equivalent resistance of everything. Still our 10-volt battery here. And R123 will be, or I guess 1 over R123 will be 1 over R1 plus 1 over R23. So let's work that out. So 1 over R123 will be 1 over 1, that was R1, plus 1 over 5, that was R23. Okay, so then 1 over R123, if we put everything over a common denominator, we're going to get 6 over 5 here. So if we flip it, R123 is 5/6, which is about 0.83 ohms. Okay, so our equivalent resistance here is less than any of the resistors in the system, which makes sense. And so now we can kind of start working backwards, because now that we know the equivalent resistance, we can figure out how much current is flowing through the circuit, or at least flowing out of the battery in this first bit before it gets to any of the junctions. So the way we would do that is to say, let me define the current I here. So we know now that there's 10 volts passing through R123 in this equivalent circuit, and the resistance we know is 0.83. And so the current that's flowing will be equal to, according to Ohm's law, the voltage 10 volts over the equivalent resistance 0.83. And so we're going to get 12 amps of current flowing. Okay. And now if we work backwards, so now we work backwards up to the more complicated version. We have a little bit more information now, and now we can figure out what we're doing here. So now we know that there's 12 amps of current flowing this way. And we know that that current will split here. So there's I1 in this leg and I2, 3 in this leg, I'll call it. Okay. And we know I1 plus I2, 3 has to add to 12. But we also now know that the voltage drop here from this side of the circuit to this side of the circuit is 10. We still know that. And so we can figure out the current using these resistor values. So let's figure out the current using the resistor values that we have. So I1 is going to be the voltage 10 volts over R1, which was 1. So 10 amps of current passing through the first resistor. And we can figure out I2, 3 in 2 ways. One is to just know it has to be 2 amps, because that's the difference between the total current 12 and the current through I1, 10. Or we could use Ohm's law again and say I2, 3 is equal to 10 volts over 5, which is the equivalent resistance R2, 3. And so 2 amps. And those add up to 12, so that checks out. Okay, so now we work backwards even further, and we now know that the current here is 10 amps, current here is 12 amps, and the current here is 2 amps. And the last thing we would need to know about this circuit is the voltage drop across R2 and then across R3. That's the last thing we don't know about this circuit. So if we wanted now V2, that's going to be equal to current times resistance. So 2 amps times 2 ohms equals 4 volts. And now we can get our V3, excuse me, in two ways. One is to know that the total voltage drop has to be 10. So therefore V3 has to be 6 because there was 4 across R2. The other way is just to do the same technique here, where we have 2 amps of current times 3 ohms of resistance equals 6 volts. Okay, so we now know basically everything there is to know about this circuit. We know what the current is everywhere, and we know the voltage drops across each of the resistances. Just to add on V1, we know V1 has to be 10 because it's in parallel with the battery. So we know that. So we know V1, V2, V3, we know the currents through each section of the circuit, and we know everything. That's an example of how you can use these series and parallel ideas to do circuit analysis, and I hope it was helpful. Okay, bye.